Hey everybody, Dr. A here, and in this video we're going to be exploring another virtual work example, this time calculating a beam rotation angle. So let's go ahead and get started. In the given information, we're being asked to compute the slope angle, also known as a rotation angle, at point B. And we're being told that the flexural rigidity is constant for this beam. So here we have a cantilever beam. The free end is A. We have this intermediate point B that we're interested in. And then the fixed point is C back here. Now, point B, the point that we're interested in, there's nothing really special about this point other than that's the one we're interested in. And it's located right in the midspan of this 10-foot or 10-meter long beam here, okay? Now, the free end has a 3 kilonewton point load on it, and that's the only real load present. So let's go ahead and get started on how we're going to tackle the solution for this problem. If I write solution, the first thing I want to note is that the flexural rigidity is constant. We were told that right here in the problem statement. Flexural rigidity is constant. What does that mean? Well, the flexural rigidity is the product of E and I, so we're saying EI is a constant, okay? So that just means that, once we take some integrals later, we can pull these terms out of the integrals, okay? The next thing we want to note is that we're going to need two x-coordinate systems, okay? So let's make a note of that. We need two x coordinates, okay? Or we could think of this as two domains. Why is that? Well, the reason is because the point that we're trying to find the slope angle at is point B right here, okay? Now, the real load is at point A, so we need to capture what's happening in both of these domains, from A to B and at B to C, because the point that we're interested in finding something out about is at a different point than the only real load, okay? Now, another thing I like to do a lot of times is to help me visualize what this deflected shape is going to look like. I'm going to draw the elastic curve here, the deflection diagram here, just to help me visualize it. So that's going to look something like this, right? It's going to be this kind of polynomial curve, or this, curved deflection shape, right? So let's try to draw it again a little nicer. Oh, that is not right. So again, it's this kind of polynomial curve. I'm trying to draw it kind of exaggerated a little bit. Keeps locking on to a straight line. There we go. Something like that, where we have a taper right here where it flattens out back to zero. Now, at point B, what am I really interested in? Well, at point B, I'm interested in a tangent line that's going to be tangent to point B, okay? So if I draw a line that's maybe right there, tangent to point B, and then I put a horizontal reference line here, what I'm interested in is this angle right here, okay? And that'll be, theta sub B, okay? So, and again, we're using virtual work to do that. So let's go ahead and turn to the next page, and let's go ahead and begin our analysis. I'm going to start by analyzing the virtual beam, okay? Now, when I draw the virtual beam, what am I going to do? Well, I'm going to go ahead and redraw the beam itself. Here's that fixed connection. And I'm going to go ahead and place the virtual unit load at point B. Now, this is going to be a moment of magnitude 1 kilonewton meter, okay? Remember, you place a virtual unit moment whenever you're looking for a rotation. I'm also going to need to define some x coordinates. Here's going to be x1 and here's going to be x2. So again, defining those coordinates, especially when there's one not given to you automatically. So some problems will have those x coordinates already given to you in a textbook, for example. If not, you just define one yourself, or in this case, define two ourselves, okay? So now what we're going to do is use method of sections, and we're going to get the internal moments in each one of these domains. So I'm going to say, make a note over here, I'm going to say use MOS to get virtual little m moments on each domain. Okay, so I'm going to say cut 1, and this is going to be in the first domain. So I've got my cut section here, and here is x1, and I'm going to go ahead and sketch on here. Let's use maybe purple. Here is little m1, okay? Now, obviously, there are no loads here, right? If I'll just look at this three-body diagram, there are no applied loads, so clearly little m1 is going to be 0, okay? Now I'm going to make a cut 2, and while I'm sketching this three-body diagram, if you want to go ahead and maybe tell it out loud what M2 is going to be, because hopefully you can just look at it and figure out what M2 is going to be. Here's that applied load, 1 kilonewton meter. And let's draw some dimension lines on here. Let's draw them a little bit better than that. Here we go. That's 5 meters. This is going to be x2. And then, of course, here's M2. So here I can say sum of the moments about the cut equals 0. And then clearly I'm going to have 1 kilonewton meter plus M2 equals 0. And so M2 is equal to -1. Now, before I move on, do I have a shear force at these cuts? Is there a V1 and a little V2 here? Yeah, absolutely. There's definitely a shear force there, but we're not interested in the shear force for virtual work. So you could draw it there if you wanted to. You know, you could put a little V1 there and a little V2 here, but remember, we're not interested in those, so they're not really going to come into play, so it's not a big deal if you don't draw it, but if you want to draw it for the sake of completeness, then go right ahead. So what do I do next? Well, I'm done analyzing the virtual beam. Now I'm going to analyze the real beam, okay? So let's come over here on the next page and say real beam, okay? Now, when I analyze this real beam, I'm going to redraw this real beam just to remind myself what it looks like. Here's 3 kilonewtons. Here's that fixed connection. And I'm going to go ahead and sketch on there my x1 and my x2. Just for reference, 5 meters, 5 meters. And I'm going to say cut 1. So here is that 3 kilonewtons. Here's the cut. Draw that cut dimension a little bit better for us. X1. This is going to be capital M1, right? We're going to say sum of the moments about the cut equals 0. And we can go ahead and say that's going to be 3 kilonewtons times x1 plus m1 equals 0. m1 is equal to -3 x1. All right. Now, what about cut 2? We're going to say cut 2 somewhere in that second domain. And we've got the real load, 3 kilonewtons hanging out there. And, our cut is right here. And then let's draw some dimension lines here. Let's draw it a little bit better. There we go. Here's that 5 meters. Here's a x2 there like we defined it earlier. And then, of course, this is capital M2, okay? And so we're going to say sum of the moments about the cut equals 0, counterclockwise positive. And so we're going to say 3 kilonewtons times 5 meters plus x2 plus m2 equals 0. And of course, we can say m2, do some rearranging, negative 3 times the quantity 5 plus x2. Okay, and of course, you can include the units in there as well. So now what we're ready to do is to set up the virtual work equation. All right, so in order to do that, I'm going to go ahead and change colors again. And I'm going to say 1 kilonewton meter times theta b equals the summation as I goes from 1 to 2, because we have two domains, of the integral 0 to L, little m, capital M, over EI dx, and then sub I, okay? And so I can expand this out because I've got the two domains, right? So I can say 1 kilonewton meter theta b equals integral 0 to 5 meters, little m1, capital M1, over EI dx1, plus the second integral, which is the second 5 meters. Remember, both of these domains were each 5 meters long, right? And this is going to be little m2, capital M2, over EI dx2, okay? So this first integral term is segment AB. The second integral term is segment BC, okay? Now I'm ready to substitute all of my values in there. So I've got 1 kilonewton meter times theta b equals the integral from 0 to 5 meters of 0 times negative 3x1 over EI dx1. And I think that was negative 3x1, right? Yep, that's right there. Okay. And then we're going to incorporate the second integral in here, plus integral 0 to 5 meters, negative 1 times negative 3, 5 plus x2, all over EI dx2. All right. Now that first integral is going to go to 0 because you're taking a definite integral and you got a 0 inside of that, right? And so when you evaluate this second integral, what we end up getting is the following. You get 1 kilonewton meter times theta b equals 112.5 over EI, and that numerator, the 112.5, carries units of what? It'll be kilonewton squared times meters squared. How do I know that? Well, remember, you've got this first moment function, which is going to have units of kilonewton meters, and then you also have the second moment function, which also has units of kilonewton meters, and then you've got this dx. Actually, so it's kilonewton squared meters cubed. So let me correct that. Almost made a boo-boo there. Kilonewton cube, right? And so then you can see that some of these units cancel on each side, right? So finally, our final answer is theta b is 112.5, where that numerator, the 112.5, carries units of kilonewtons times meters squared over EI, right? Because this kilonewton cancels with one of these kilonewtons, and this meter cancels with one of these meters. And this is your final answer. And what is the direction of this? Well, this came out positive, which means that this is going to rotate in the direction that we assumed for our unit load. So we assumed our virtual unit load was rotating in a counterclockwise fashion. We did all the calculations. Our final value came out positive. So that means that theta is rotating counterclockwise. And that makes sense here. This thing is rotating counterclockwise. If we go back to our original figure and look at that tangent line orientation, okay? So that concludes this example. If you found this helpful, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.